Hello, everybody. We're still talking about the distillation columns in Aspen Plus, and in this video we're gonna go kind of in more details into this part where we can choose either the equilibrium or rate based, and we have been working with the equilibrium since we started talking about distillation. Um, but just I'm not gonna go into deep details, but I just want to give an overview of what you are gonna expect or what you should do when you go for the rate-based calculations. And we will go through the tower internals because it's a very interesting part of the column. So when you do the rate-based or uh, choose the rate-based calculations, you'd see that there are two parts here that need to be fulfilled. The first is the rate-based modeling, which is, as I mentioned before, uh, when when you go for the rate-based calculations, you should take into consideration that there are mass transfer calculations that are gonna be done. This will include the calculation of the Reynolds number, the mass transfer coefficients, the flow regime, and the resistances to mass transfer. So this is what you should expect here. So these are like numbers that you can find as the default numbers, and when you go through the like the calculations deeply, you should have values for each one of these terms. Either the transfer, I don't know what's the condition factor, but the Chilton-Colburn parameter that's used to calculate the mass transfer coefficient, and there are like many things that you have to do here. And as you see here, there are something that's related to the Reynolds number, the Sherwood number for the vapor, for the liquid. A lot of details that you have to go through to be able to do the calculations. I'm not going to go through these now, but I just wanted to let you know that this is something that you have to know before you go through these. The other part of this video is going to be related to the column internals, and because this is a really interesting part of the distillation. This is something that we usually study or teach in the mass transfer undergraduate courses. Uh, so I thought it's interesting or it's useful to go through this. So when you um, go for add new, it's gonna give you this message that there are missing hydraulic data. And this hydraulic data is kind of how you're gonna start your sizing of the column, either by calculating the diameter of the column, the tray shape, the tray size, the number of holes in the trays, and all these things. So it can generate the data if you click on generate, and calculate the data for you, and you will have the option to edit them if you want. This is what the software is doing now, and again, I like to emphasize this every time. This is not an easy task. This is like a very long process, and anyone who has done these calculations manually will know how much time and effort it takes to do these calculations. So for the column internals, you'll find that this is what we have, the INT1. Um, and by going through this, you have the column, and you have to split the column into sections. Usually, the column is split based on the inputs and the outputs. So if you have like a case like this, one feed and two outputs, then there'll be a section here and a section here between 2 and 50 and between 50 and 99. If you have more than one feed or you have side products, then you will have more sections depending on how many side products or how many feeds that you have. So you can add the sections manually, or you can do auto sectioning, and by clicking on auto section, it's gonna do what I was gonna do manually. It's gonna split it into section from 2 to 49 and from 50 to 99. And here you see it's calculating the diameters and the tray spacing. And you'd see that the diameter here in the top section is greater than the diameter in the bottom section. It seems that the flow rate in the top section was higher. Um, Before going into the details, I would like to kind of quickly review with you what we care about, or what are the information that we need to know when we look at the tower internals. I'm going through the details of the tray columns. The packed column is another story, so I'm not gonna go through it now. So just as a refreshment, the tray is like a place where we let the liquid and the vapor meet. So the liquid is coming from the tray, from the above tray, going through the downcomer, which is this part. This downcomer should be high enough so that the liquid gets clear. So it's as you see here, it's like a lot of bubbles, what we call the froth, and this froth provides the large surface area for the mass transfer to happen. So the froth kind of gets stable here, and all the bubbles are gone, and the liquid goes from here to there. The gas is bubbling, or the vapor is bubbling through the small holes here. Either it's sieve tray or bubble cap, or whatever the shape of it, but there is a space for the vapor or the gas to bubble through the liquid, make the bubbles with a big surface area, and then the liquid goes down from this tray to the next tray, and the gas flows to the tray that's above. There should be enough spacing between the trays so that any liquid that is entrained with the gas falls back to the tray. So we have only gas going from the bottom tray to the tray above it. In some cases, we have what's called the split flow. If you have a large diameter column, in this case, the liquid distribution and the gas distribution kind of is not easy, or it's not uniform. So to make it uniform, you split the flow so that you have the liquid, instead of going the whole diameter, it's gonna go only half the diameter. So it's going this way and then this way, and so on. So for each tray, you have two downcomers, um, from the right and from the left, instead of having only one. Um, when operating the column, we are facing kind of challenge to make sure that the operation is optimal. So there is this dashed region of what we call the stable operation. This stable operation is a function of the liquid flow rate and the vapor flow rate. For the liquid flow rate, if it's small, then we will have what we call entrainment, so that the vapor will have the go from the bottom tray to the tray above, and it's gonna take some of the liquid to the tray above. If the liquid flow rate is very high, then we will have what's called the downflow, or the downcomer flooding. So the liquid is the flow rate of the liquid is very high, so that it's kind of filling the downcomer, and we might face what we call the choking, which is the total filling of the tray, so that the liquid cannot push the vapor. Uh, for small vapor flow rates, we will have what we call weeping, and by weeping we means that instead of having the vapor going through the holes of the tray and going up, the liquid is dropping from or dripping from the holes. So it's kind of the tray is weeping, it's crying. So that's why we call it weeping. For very high vapor flow rate, we'll have again the entrainment problem. So the optimum conditions are the anywhere inside this dashed area. So this is what we really care about when operating the column, and this is something that the software can help us with. So now we can see that the software has already generated the diameters and calculated the diameters and the tray spacing, and here we can see each one of these two sections. It's giving us information about the geometry. So it's telling us how wide is the downcomer. And we have, I didn't mention that, but we have here what we call the weir, which is this part. It kind of keeps the liquid inside, so that we have a height of a liquid enough to make the froth and to give chance for the gas and vapor to meet and to form the bubbles. So here we have the weir length. they are already calculated, so we don't need to do anything. This is again the tray spacing, the downcomer clearance, the weir height. There are like the parameters are already calculated here, and the summary of the tray geometry. Everything here is done. So it's kind of like the heat exchanger, that you have all the results by just running the file. So you do not do anything by yourself. Again, for those who have done these calculations manually, they will really appreciate what they see now. It's kind of 1 or 2 days task of calculations. So it's very nice to have everything already done. One of the nicest things also in this part of the tower internals is the hydraulic plots. And in this hydraulic plots, it's showing us if we are operating in the optimum range or not. So here you see the column is kind of having different colors. You'll see that this part has a diameter different from this part. So if I choose this region, we see this is the same figure that we have here. So this is the same as this. So it's telling us where are we operating. We are operating at this part, at this point. And this is the weir load, the entrainment, the jet flood, the weeping. So it's almost the same thing that we mentioned about the considerations while designing the column. So here in this blue part, we are fine. We don't have any issues. Here we are starting to get very close to the entrainment part, so it's not very safe to operate here. Here we are coming out of the range, so we have entrainment issues while working here. So this is not something that is good to operate. So here again it's very close, and here we are out of the range. So it's kind of telling us where the problems are. So I can try to fix it by changing the flow rate, or by changing the weir or the diameter of the holes of the tray. So there are many parameters that we can play with. I'm not gonna do this now because this is not the purpose of this video. But in case you are interested, you can check a textbook that's called Colson and Richardson. It is in volume 6, as I remember. There is a detailed procedure for design of the distillation columns and doing the checks, and for each case or for each issue like this, what solution that you can follow to get the column to operate in the optimum conditions. So this is something that I really recommend you to do, and I hope it helps. So I think this is all for this video, and I'll see you in the next video, inshallah. Goodbye.